Alrighty folks, in our 60th installment here, we're now still trudging through Unit 7 on quadratic functions. Very important unit though, a long one, but an important one. We're looking at the equation of a quadratic in standard form, and we're just sort of going to develop ourselves a little formula for finding the vertex and the axis of symmetry. So that's the first thing, is to get that formula, and then we're going to use the formula to help us find the coordinates of the vertex of a parabola. Here we go. All right, so for the first one, all I want to do is I want to look in each case here, already given you a graph and an equation that corresponds to it. So this is the equation that would produce that graph, and I used computer software to do that. And I've already drawn the axis of symmetry through each graph, and I've given you the x-coordinate there. So what that equation is for that axis of symmetry. Now what I want to do is I want to take each equation, I want to list the values of a, b, and c from the equation. So for the first one, we have a -1, a 2, and a 3. Okay, so then I want to take this magic little formula that we don't need to know how I derived it, but I just want to see what happens if I take x is equal to -b divided by 2a. So that's going to be here, the negative of 2 divided by 2 times -1, and I think that all works out to be a +1 when I do that. Okay, so I get x equals +1 for this guy. For the next one, I'm going to do the same thing. So my values for a, b, and c are 2, 4, and -3. And now I'm going to take -b divided by 2a, so that'll be -4 divided by 2 times 2. And I think that gives me a -1. So I get a formula x equals -1 for that guy. And for the last one, my values of a, b, and c will be -1/3, -2, and +5. So if I take x equals -b over 2a, that's going to be the negative of -2 over 2 times -1/3. Okay, so the negative of -2 is a +2, and those 2's can cancel. So I'm just going to say I have a +1 divided by -1/3, multiply by the reciprocal. 1 times 3 is 3, but it's negative. So here I get x equals -3. And what you'll notice is that for each case, when I use that little x equals -b over 2a magic formula, it comes up with exactly the equation of the axis of symmetry. That's convenient. Let's see what happens now. If I remember that my axis of symmetry is x equals -b over 2a, let's try this example that we have right here. I'm hoping that if I try that formula, it should tell me my axis of symmetry should be at x equals 2 right down the middle here. Let's see what happens. We have x equals -b will be the negative of -4 over 2 times a, which in this case is 1. So on the top I'm going to have a +4 divided by 2, which is a +2, which is exactly what we wanted. So since x equals 2 everywhere along that line, let's grab this point down here at the vertex. Remember, its x-coordinate and its y-coordinate are the coordinates of our vertex. And since the line x equals 2 goes right through that, and x is actually equal to 2 everywhere on that line, our x-coordinate is going to be 2. Aha! So the x-coordinate at the vertex could follow the same formula. So whether I'm looking for the axis of symmetry or the x-coordinate at the vertex, it's always x equals -b over 2a, which in this case turns out to be x equals 2. The real mystery is, well, how would I get the y-coordinate? Well, if I go back here and I look at my equation, remember what that equation represents. It's a relationship between the variables x and y. For any point on that parabola, I can get the y-coordinate by filling the x-coordinate that I have into the right-hand side of the equation. So if I were to take my x value of 2 and plug it back in that equation, I should get the value of y that I want. And that's exactly what I'm going to do here. So here I'm going to take the x value I had of 2 and plug it into both of those places where x was in the equation, there and there. And then I'm just going to calculate what y would be. So 2 squared is 4. 2 4s are 8 that I'm subtracting, and then subtracting 3. So 4 minus 8 is -4. Subtract 3 looks like a -7. So that tells me my y-coordinate should be at -7 when my x-coordinate was at +2. Oops, -7, isn't it? Let's cross that off and write it again. So we got 2 and -7, and they should be the coordinates of our vertex. If we look over here, it's not hard to read that those coordinates are 2 and -7. Whoops, I did it again. So what we have is a formula that helps us get the x-coordinate at the vertex, which is equal to the equation of the axis of symmetry, and then we just plug that in to get our y-coordinate. Magic. So The only thing that's left to answer is, if I didn't have my graph, how could I tell whether that value I had at my vertex was what we call a maximum, or as it was in this case, a minimum value at the bottom of the graph? Well, using the formula that we just had, combined with what we know about the value of A, being positive opens upward and negative opens downward, now we can tell you whether you have a minimum value. So if A is positive, happy, and we open up, we're going to have a minimum value. But if A is negative, sad, and it opens downward, we're going to have a maximum value. So we should be able to determine directly from the equation the axis of symmetry, the coordinates of the vertex, and whether or not that y value, the function value at that vertex, is a maximum or a minimum. Nice. Putting all that together in a hurry. Quick summary. So we find the axis of symmetry using the formula x equals negative b over 2a. This gives us the x-coordinate at the vertex. The y-coordinate can be found by substituting the x-coordinate back into the equation. The sign of the leading coefficient, a, determines whether the function opens upward or downward, as we know, and if the graph opens upward, the y-coordinate will be a minimum. If the graph opens downward, the y-coordinate is a maximum. Awesome. So, some quick practice questions with that in your next installment. Good luck. Thanks.